So in this video, we're going to look at example 5.13 from the homework. And we have a beam that's loaded with a distributed load, and we're given some parameters that define the actual load distribution. And what we want to do is determine the y component of the reaction at A and the x and y component of the reaction at B. Now, one thing I'd like you to think about before we dig into this problem is why does the B reaction have an x component, but the A reaction doesn't? So hopefully you've gotten some experience both from looking at the lecture last week, along with doing one of the homework problems that ask you to kind of consider the various types of reaction forces that supports can provide, that since the actual support at A is a roller, it can oppose any forces that are applied in the horizontal direction. So it can only oppose forces which are actually applied in the vertical direction. So this will not have any horizontal reaction component. So you can kind of imagine like something sitting on a roller. If you push it to the right, it's going to roll. It can't oppose that force. So the only reaction that it can oppose is if you push it down. So its reaction will be purely vertical. However, this pin connection at B, if you think about it, if you try to push it to the right, it can oppose that because it's actually pinned in. It can also oppose vertical forces as well. However, if you think about something that's pinned, it can still rotate. So this type of support structure can oppose both vertical and horizontal forces. This kind of support structure can only oppose vertical forces. So when you talk about the unknown reactions, that's why this only has an x component versus this has an x and a y component. So even though we ultimately have to draw a free body diagram, what I'm going to do for my first step is to replace the distributed loads by a single concentrated load. So I'll say step one, replace the distributed by a concentrated load. And if you remember the way that that works, I think it was about 2 weeks ago that we actually talked about this, is we need to take the actual distribution and we need to find both the magnitude of the actual single equivalent load or concentrated load along with the point of application. So I'm going to start with W1. And if you notice W1, the actual load distribution kind of looks like this. So it has a taper to it, but it only goes down to some minimum value. It doesn't taper all the way down. So let me actually get this drawn in and hopefully you'll see what I mean. It has a peak value of W1, but it only decreases to W2. So this is W1 and this is W2. So what I'm actually going to do is to break this distributed load further down into two parts, the uniform part and the triangular part. So just so I'm clear, I'm only talking about the portion of the load that's from 0 to 3 meters here. So I'm going to show it like this. And I'm only going to, rather than draw the actual arrows, I'm just going to draw the shape. So those should actually be the same. Let me actually redraw that a little bit just to make it look a little bit clearer. Those should be the same width because it's like this is stacked on top of each other. So the first thing that we need to do for both of these is actually determine the magnitude of the equivalent force. And remember that the magnitude of the equivalent force is equal to nothing more than the actual definite integral of that distribution over the area which it's applied. So in this case, it would be from 0 to 3. However, up to this point in the text, we're going to, rather than actually compute the integrals, we're actually just going to find the area under the curve of both of these distributions. Now be careful with this, because when you think about how tall the triangular part is, yeah, it has an actual peak value of W1, but the triangular part, we're accounting for the W2 part in the uniform part. So it goes down to actual W2. So when you talk about the height of this triangle, in terms of finding that area under the curve, the height is going to be W1 minus W2. So remember, for a triangle, it's always 1/2 the base times the height. So I'm going to say it's 1/2. Now, what is this actual base dimension here? Well, if you notice, this portion of the load is applied over a 3-meter span. So the base is going to be 3 meters. And then the actual height here is going to be W1 minus W2. And you can look at the actual units of that if you want, but it's going to be the force density, which is going to be in newtons per meters. So when you actually compute the units of this, it will be in newtons. So if you compute what that is very quickly for our actual parameters, it's 1/2 times our W1 is 990 and our W2 is 660. And that is, we also need to multiply, that's the height. We also need to multiply it by the base. So it's going to be 1/2 times, what will that be? 330, and then you're multiplying by 3. So let's check our math on that. So 990, I'm going to type it all in just to make sure that we don't make any mistakes. 990 minus 660, that is a height, times 1/2, and then times the base is going to be 495 actual units here of newtons. So that's step one. The second step is determining where we actually apply that force. And remember that we're going to apply it, so this is the equivalent magnitude. The second thing we need to consider is where to apply. And if you remember, during that lecture, we showed a table and we talked about a table in your book where you can actually find the centroid of these shapes. And for a triangular area, it's just going to be at, if this is the entire base, we're going to apply it at 1/3 the way from kind of the thicker edge of the base. So in our case, that triangular load density is distributed over 3 meters. Let me actually zoom this in all the way just to make it a little bit easier. 3 meters. So 1/3 of 3 meters is just going to be 1 meter. So I'm going to replace this triangular portion of the distributed load by a 495 Newton force applied 1 meter from the actual edge of this beam. So now we need to do the rectangular part. And it's going to be a little bit easier because the area of a rectangle is just going to be the height times the width. Remember that the width is the actual 3 meters over which that rectangular portion of this load is distributed. And the height is just going to be W2. So when I compute what this equivalent magnitude will be, it's going to be nothing more than 660 newtons per meter, I should say, times a width of 3 meters. And if you multiply 660 by 3, sorry, it has been too long a day to do this in my head, it's going to be 1,980 newtons. So again, that's just the area under the actual rectangular portion of this load. We broke the section from 0 to 3 up into a triangular and a rectangular part. And then the actual point of application is going to be the centroid for a rectangular area is just going to be half the base. So for the case that the base is 3 meters, like we have here, it's going to be 1.5 meters from A. And I should have wrote this as 1 meters from A. So we've replaced the kind of triangular plus rectangular portion of the load by 2 equivalent single forces. So the last thing that we need to do is to do the second part of the distributed load, kind of the portion that's just rectangular. So I'll say for the portion, so let me write this in. This is for the portion from point A to the middle. And for the portion from the middle over to B, it's just going to be a purely rectangular load. It is also 3 meters wide, if you look at the diagram that you're provided, going from there to B, and its height is just going to be W2. So in terms of the magnitude of the equivalent force, it's just going to be W2 times 3, which we already did above. If you think about it, the rectangular portion of this rectangular plus triangle had the same parameters. So it's just going to be 1,920 newtons, 980 newtons, I should say. So that same calculation that we made up here. And its centroid is also going to be at the halfway point of the actual distribution, but it's not going to be like in terms of it's halfway in this rectangle. So it's going to be 1.5 meters from B, or equivalently, if you were to measure it from point A, it will just be 6 minus 1.5 meters from A, which is just going to be 4.5 meters from A. Or an alternative way that you could write it is 1.5 meters from B. So the key thing that we did there is we had the information that we need in order to replace the distributed loads by single equivalent forces. So now that we have that, we can actually draw a free body diagram. And the way that we will do that is we will just separate our beam from its supports. As we were told in the problem description and as we argued earlier, the reaction at A can be replaced by a single vertical reaction. And what that is saying is that when we, for this loading that is shown, what we'll find is that the actual horizontal component of this force is 0. But for this loading, if we were to remove it from that roller support, we need to account for what the roller support does to the beam, and that actually pushes it up. In a similar fashion, we can draw in the two reactions at B. That pin connection is going to serve to push the beam up and kind of counterbalance it being pushed down. And it also has the capacity to exert a horizontal force. So you can call this RBX, and I'll call this RBY. But what we're going to see, hopefully very easily, is that this must be equal to 0. And we'll prove that in a minute. But the next thing we want to do is actually replace both of these portions of the distributed load by the equivalent forces associated with them. So if you think about it, for the portion from 0 to 3, we found two equivalent forces. We found the portion associated with the triangular force, which is 495 newtons in magnitude, and it's actually applied at 1 meter from point A. So I'm going to draw that in first. So I will call this 495, and it's 1 meter from point A. And then the second force, and this isn't going to be to scale because I'm going to need to kind of separate these out a little bit, is going to be the rectangular portion of that. And it's going to have a much larger magnitude, 1,980. And I'm going to draw that by like a larger vector. You don't have to, but the main reason, to be frank, that I'm doing it is that way I can mark in what this distance is. And if you remember, we applied it halfway throughout the load distribution. So the rectangular portion of this was 3 meters long. So it's going to be applied 1.5 meters from A. So this is 1.5 meters. And then finally, the portion of the distributed load from the midpoint to point B, we also determined how we would replace that by an equivalent, where are we at here? Just trying to force my work. This is kind of, I'm going to draw on a dashed line. So that's everything that we did here. And we showed that it is also corresponds to a 1,980 Newton force, because it had the same area as the rectangular portion here. And it was actually placed 1.5 meters from point B. And this entire span of the beam is 6 meters long. So let's talk about the actual how we would solve for these unknown reactions. So remember that in general, for a coplanar force system, you can write 3 equations of equilibrium. In general, you can sum all forces in the horizontal and vertical direction, and you can compute a moment about 1 point. However, as I mentioned in that lecture video that I recorded, those are not unique. Those aren't the only unique equations you can take. You can also take 3 rotational-based equilibrium equations. So I could sum moments about 3 points. In general, you want to pick whatever equations of equilibrium are easier in order to let you solve for, most easily, the 3 unknowns of interest. So in this case, they are the horizontal RBX, RBY, and RA. So the 3 that I'm going to choose to enforce, and you'll see why I'm going to do it in a minute, are I'm going to sum all forces in the x direction and say those have to be equal to 0. And I'm going to have horizontal right be what I'm calling the positive there. I'm going to sum all moments at point A and set those equal to 0. And I'll have the standard counterclockwise positive convention there. And I'll also sum all moments at point B and set those equal to 0 with standard counterclockwise positive convention as well. So why did I actually choose these equations? So I'm going to number them 1, 2, and 3. Well, what do you notice if you sum all forces in the x direction and set that equal to 0? Well, the only force that exists in this free body diagram in the x direction is that potential reaction at pin B. So all that's showing you is that for this particular loading condition, although the pin reaction at B could oppose horizontal translation, it doesn't have to, because the entire loading condition is just purely vertical. So that reaction there is actually 0. Now let's talk about summing all moments about point A and what that actually does. If you think about summing all moments about point A, remember that the way we do that is we pin the actual body at point A, and we look at the rotation caused by all the forces. So if you think about, sorry, I have some papers in the background there. If you think about the rotation that's applied by the equivalent 3 forces that represent the loading distribution, they're actually going to induce clockwise rotation about point A. And that's going to be opposed by the vertical reaction at B in the upward direction, which is going to introduce counterclockwise rotation. I'm going to move it that way I can actually move my paper. So what's happening is the tendency of these three forces to rotate in the clockwise direction about point A is counterbalanced by the tendency of the reaction at B in the vertical direction to rotate in the counterclockwise direction. So by summing all moments about point A, that allows me to get an equation that isolates the vertical reaction at B, RBY. So it's just a convenient choice for solving for one of the two reactions I need. So let's actually compute what this would be. Well, as we kind of justified earlier, all three applied loads are going to tend to induce a clockwise rotation, so they're all going to be negative. And the perpendicular distances, since they're all vertical, are also pretty easy to see. Relative to point A, this is 1 meter away, this is 1.5 meter away, and this is just, if the entire beam is 6, and this dimension is 1.5, it's going to be 4.5. So what I'm going to write is minus 1 meter times 495 newtons. So this is all in Newton meters. You don't have to show your units if you don't want. Minus 1.5 meters times 1980 newtons minus, what would this perpendicular distance be? Remember, the entire distance is 6. This is 1.5. So from point A, that is 4.5. So 4.5 meters. Also times 1980 newtons plus the unknown reaction that we have, RBY, is actually 6 meters away from reaction A. So since it has that large lever arm, it's not going to have to be as large as it might have to be in order to oppose all of these rotations. So it's just going to be plus 6 meters times RBY, and that whole thing better equal to 0. And what that's going to tell us, if you do your algebra there, is that RBY is going to be, in the numerator, you're going to have 495, I'm going to drop my units, times 1. That is the rotation about point A caused by the triangular portion of that load on the left side, plus 1980 times 1.5, plus 1980 times 4.5, and then that will all be divided by 6. So if you determine what that actually is, and let's compute it here. So it's going to be in the numerator at 495 plus 1980 times 1.5 plus 1980 times 4.5. And I'm going to take all that and divide by 6. And sorry about that. A little bit of a typo there. Let me recheck all my entry here. 495 times 1, that's right. 1980 times 1.5, that is good, plus 1980 times 4.5. And I'm going to take that all and divide by 6. And my answer is giving, my calculator is giving me an answer in scientific notation. That is 2.0625 times 10 to the third in whatever units that would be in. And notice that all of our forces were in newtons and all of our distances were in meters. So this is in newtons. And more commonly, I'm going to absorb this factor of 10 to the third and write it as kilo. And if I write it as 3 sig figs, like your book traditionally likes it, that will be 2.06 kilonewtons. So that is the vertical reaction at point B. So how will we get the expression for the vertical reaction at point A? Well, there's two different ways that you can do this now. You could sum all moments about point B, and you might want to practice doing that. Or another thing I would tell you is usually if you only want to write one moment equation, I think it's good to write 2 at first until you get a practice with it. You can just sum all forces in the vertical direction. So I'm just going to do that to make this video a little bit shorter, since I know it's getting a little bit long-winded. And all that this is going to show me is that all the forces down have to equal to all the applied forces, which go in the negative y direction, have to equal the sum of the two reactions, which go in the upward direction. So you can show this as RA, and I'm just going to call, actually I'll keep my notation consistent, RBY. Those are the two forces going upwards, and those have to oppose the 495 down and the 1980 down and the 1980 down. Those all sum to 0. So another way that you can write this that actually looks a little bit better is you can show that if you take and add 495 plus 1980 plus 1980, so that is the sum of all the downward vertical loads actually applied by those distributed loads, and you subtract away RBY, that gives you RA. So what this is saying is however much loading there is in the vertical direction, whatever RBY didn't take care of, RA has to take care of. So it's the total load minus whatever RBY is already taken care of. So that's just going to be all of this. And then we're going to subtract away the 2.06 kilonewtons. So let's see what that turns out to be. So I'm just going to say 1980 times 2, since there's two of those factors, plus 495. And then I will subtract away my answer, which is stored as a variable in my workspace as ANS. And that will actually turn out to be 23 sig figs again, 2.39 kilonewtons. And sometimes your book will actually show an arrow to indicate the direction, but we assumed that all of these forces were vertical. It wasn't much of an assumption because we knew that they were reactions counterbalancing downward forces. So since our direction assumption was correct, these all turned out to be positive, and that means that they go in the direction shown on the free body diagram, which is in the upward direction. So hopefully that was a good practice in terms of both replacing distributed loads by single equivalent concentrated loads, and also enforcing equilibrium equations in 2 dimensions.